Let us have a short look at this solution to this exercise. So here I have the code that you can see in my document, the suggested solution code. And what is it that we are doing here? Well, first of all, we load these packages here. The first one, tidyverse, we almost always use. The second one is needed because we want to read some FASTA files, right? Using this read FASTA function. And here we read the FASTA file with the contigs. Then what we immediately do here now, after we have read it in, we don't even store it in an object. We just pipe it directly into the next function, which is mutate. And mutate we use to either change an existing column or add a new column. And it's the latter we do here. We add a new column called length. And we add it by using this word function, picking word number 4 from the header texts. So if you read in this table, and let me do that. Let me stop the pipeline here and just make it a small table here. So we just run the code down to here. First of all, make sure you run the code in the working directory where the file is. This is usually a good idea. It's not actually necessary, but it's usually a good idea because then files and everything are where you think they are. Because notice here now we read the file. This contigs file must be now in the same folder where we are running the R script, right? The working directory. So look above at the console window, find the console window, look at the path here, and even click on this arrow to make the files window show you the content of this exact folder, right? And here I can see I have this file in this folder that I'm looking at here on the left hand side. This is the file, right? You can see the same name. And also inside this folder I have this spades underscore contigs.fasta. Otherwise this will not work. Okay, so let me just run this single line of code. I put my cursor here and click the run to read that table, and then I have it here ready for inspection. And of course, a FASTA file always has 2 columns. Right? After we read it with read FASTA, it's a table with 2 columns, and it's the header column that we are interested in now. So the text here is a little bit small. Let me look at it here instead. We can inspect the start of a table like this, typing head and the table name. So here we can see how this header text looks like. And notice there is a pattern here, right? All of them follow the same pattern. They always start with the word node, then an underscore, then a number, which is just 1, 2, 3, 4, 5, and so on, contig number, then another underscore, and then the word length, and then another underscore, and then the actual length, which is a big integer, of course. This is the length of the contig, right? So this one is like 500,000 bases long. Then cov, which is the k-mer coverage, and here comes the and here is the actual k-mer coverage. So this is k-mer coverage average for the whole contig, right? So we have looked at k-mer coverages in the previous module, so we know a little bit what it is. And it's not an integer because it's an average of all the k-mer. I mean, you count the k-mers in that contig, right? Like we did with jellyfish in principle, and then you compute an average of all. So based on this pattern, and this is very typical in bioinformatics, we need to sort of extract information from texts that follow some kind of a pattern, and not only in bioinformatics, but in data analysis in general. This is very important to have the capability of seeing that there is a pattern here and have the tools for extracting what we want from this text. We want these numbers, these numbers here, right? These are the lengths. And these are word number 4, if you count words as everything between the underscores. This is word number 1, right? This is word number 2. This is word number 3. And here is word number 4 in this text. And then we also want word number 6 in this text. Because all the text has 6 words separated by an underscore. And this is exactly what we do with this function here. We say, give us word from header column, from all the text in header column, word from number 4 up to number 4, which is word number 4. And we also have to specify that the separator symbol that separates words is this underscore. The default is to look for spaces as separator symbols. This function word will by default look for spaces, but that's not a good idea here, because then everything is one long word, right? There is no space here. And also notice that we use the as numeric, because when you extract this part of a text, it is still a text. It's not a number, it's a text. Right? So it's a very big difference between the value 10 like this and the text 10 like this. These are two different entities. The first one you can use as a value and add and subtract and multiply and so on. This one you cannot. This is just a word, you could say. It's a text that has no meaning and it has no value. So remember always when you extract numbers sort of from text, you have to actually convert them to numbers. So this part here becomes a text, right? And then we immediately just convert it to a number like this. So as numeric, or for instance this text here becomes a number without the quotes, right? So now it's a number. Yeah, and then we do exactly the same for the K-mer coverages, except we look for word number 6 instead of word number 4. And that's because we can see that, right? You have to understand that you have to look at these header lines and see this pattern and understand that this is how I can get hold of this information. Okay, so let me just go back here and add the pipe again. So if we run this one now, we will have read in the table and added these 2 columns and stored it under the name contigs, right? So if I open here now, the contigs table, it should now have the same 2 columns as we saw previously, but these 2 added. And now if we make a head here of that contigs table instead, we will now see, and this is a little bit important, because when you see a table here in the viewer, you don't really see if for instance this is numbers or texts, right? It looks the same here because there is no quotes around text. This is surely a text, right? But there are no quotes here, right? So then it's better to inspect it here in the console window using this command head, because notice here now the first column is called header, and underward it says CHR, character. This means text. So this is a text column. And the next column here, CHR, this is also a text column. But the third column, length, DBL, is for double, which is floating number. Or it could be integer, right? And this one is also double. And we can see that they are floating numbers, decimal numbers. So we can see these are numbers now, not text. We couldn't see that over here. Okay, and then we were told to compute this N50 statistic. And here is the code for doing it. First, we need to sort all the config lengths, right? And here is one way. You can do this in many ways, but this is just one way of doing it. I use the sort function to sort the config's lengths, right? So notice how I now use the table name, $column name, to refer to a whole column. And I want to sort it in decreasing order. So I have the biggest value first. So if I run this one, I think in fact they are already sorted in this order. If you look at the table here, you can see that the length, and this is because the output from Spades is already sorted this way. So it is actually sorting in decreasing order, but I don't take my chance on that, so I do it myself. In case there are some configs down there who are not in the sorted order. So now the sorted length should just be a vector of all the lengths, right? And here we can see down here, sorted length, 182 elements. And then we compute the total length as just the sum of all the lengths. And then the cumulative length as the cumulative sum of the length. So what is this cum length? If we look at the first like 5 elements, you will see that these are the first elements accumulated lengths, wasn't it? Yeah. So the first value here in the cumulative is the same as the first length. And then we can see the second length is shorter, but here it's bigger because it's been added to the previous one, right? So this is the sum of the first 2 lengths. And this is the sum of the first 3 lengths. And this is the sum of the first 4 lengths, and so on. So element number 5 here is the sum of the first 5 lengths. That's what cumulative sum means, right? And then this line here is a little bit tricky, because here we use some comparisons. So what do? First, we look for all the cumulative length who are larger than half the total length. Can you see that? So if I copy this out here and run it, it will produce a vector of logicals, right? So we can see now the first elements are false, and from here it starts to be true. Because this is a number, right? Half the total length is a number. And now we take each element in this vector here, each value in that vector, we saw them up here, so the first 5 of them, and test sort of against this. Is this bigger than half the total length? No, it's false. This value is not bigger than half the total length. And then we go to the second element. Is this bigger than half the total length? No, false again. And then we go to the third element. Is this bigger than half the total length? False again. And also here, false, but here it's true. This one is bigger than half the total length. And all the rest are also then bigger because they become bigger and bigger and bigger values, right? In this cumulative. So actually here we have the switch. Config number 4, if we add the first 4 configs, it's not bigger than half the total, but if we add the first 5 configs, it is bigger than half the total length. And what do we do with this which function? Which will now indicate which elements in this vector are true. So if I run a which around on this one. So remember what the output from this statement here is this vector here of true and false. And which will now just give me which elements were true. And then you can see it's element number 5, 6, 7, and so on, right? Not element 1, 2, 3, 4, they were false, but from element 5, 6, 7, and so on are true. So that's the only thing the which function is doing. And then I take the minimum of these, right? So we have this vector here, and the minimum is 5. So actually when I run this code here, zap, this object IDX just contains the value 5. And why is this important? Because now I know that this is the config I should look into and store the length of. This is the N50 value, the length of this config, right? So N50 is actually length number 5 in this sorted length. And that's the definition of the N50 value. The length of the contigs where we sort of cross from false to true here. This one, right? The first true, which is contig number 5, and the length of it is 326,000, blah, blah, blah. Yeah. Okay, and here we have some plotting of this results. And here I have now plotted each config. We now plot each config as a dot in a coordinate system consisting of k-mer coverage and length. Because remember, if we go back to the table here and look at the table, at the contigs table, each row is a new config, right? So each config has a length, and each config has a k-mer coverage. So then we can of course make a coordinate system with one length axis and one k-mer coverage axis. And since all contigs has both length and k-mer coverage, we can plot each config as a dot with one coordinate along each axis. And that's exactly what we do here. So let me just run this figure and print like this. Yeah, so now I have k-mer coverage along the x-axis here and config length along the y-axis. And it doesn't matter if you switch them. Flip which one is the x and which is the y-axis, doesn't matter as long as you just could keep them apart. Okay, so what do we see here? One dot for each config. So there are 182 contigs, 182 dots, right? And notice that first config length, that's the y-axis here. We have some long contigs, and notice that this has been log scaled, so it's quite big. This is 100,000, right? This is 100,000 bases. So some contigs are very long, and many contigs are very short. So here we are less than 1,000, and here we are down to 100, right? It's almost one single read, right? This is very short contigs. And now we notice that all the longer contigs here, they have also pretty much the same k-mer coverage, right? And that's reasonable because these are contigs. I mean, the k-mer coverage, if you have no repeated regions, the k-mer coverage should be more or less the same for every config, right? It will vary a little bit, of course, because first of all it varies, and you take the average and so on. These are different lengths and blah blah blah. So some variation we will tolerate, but not super much. And we can see that there is sort of a belt here of contigs, long contigs, also with more or less the same k-mer coverage around, yeah, it's difficult to say, 40, 50 something, 30, 40, 50. Yeah, it's log scaled, so it's difficult to halfway between 10 and 100 is not the linear halfway. But we see also we have a huge number of contigs down here. And these are coverage 1, right? Or even below 1, smaller than 1, and they are short. These are almost certainly made up of error reads, I would say. This is rubbish. This is reads who have errors in them, and these are small contigs that result from these bubbles in the De Bruyne graph. So these are surely rubbish. We can throw them away. Also, we have down here some very short contigs, even if they have pretty good K-mer coverage. These are probably also dubious, right? Because they are so short. They can be used, but they are not going to be very useful to us. And then we have out here, and particularly out here, I would say, some contigs of some length. They are not super short, but they have much higher K-mer coverage. And these could very well be contigs with with some repeated region, right? They could be a repeated region since they have higher K-mer coverage. But these are the high quality ones, I would say. These ones are the high quality. So if I am going to sort of use this information to sort my contigs, I would say keep the ones who are in here, have a length above 1,000 or something like that, and also then a K-mer coverage from 10 to 100, right? If I'm a little bit tolerant here. So K-mer coverage should be more than 10, but less than 100. And the length should be over 1,000. Then I will collect all these contigs here. So this is why a plot like this can be of some importance. So now I have run Quast on the spades or original results, and also on this pre-processed spades contigs, right? We did spades twice here. First, just using the data, raw data as it is, producing some contigs, and then I wrote Quast on that one. And let's have a look at the report from Quast here. And this is how it looks like. And we can see that the genome fraction is 98.74%, right? So it's we cover close to 100% of the genome. We have a reference genome here, right? So that's why we can have this value. And here we can also see how the length of the contigs distribute, right? We have some very long contigs at the beginning, and then it's getting smaller and smaller, but we quite quickly reach like almost 100%, right? So this figure here is actually, we don't need this N50 value as long as we have this figure here, because the steeper this climbs, the larger the N50 value, right? That's basically what it says. So let me go back to the results we got from the after pre-processing, right? So this is here, and let me open this report as well. So if we now compare, this is how it looked like originally, and it has 98.7%, and here is after pre-processing, and you can see it's basically the same value. It hasn't changed, right? It doesn't cover more of the genome now, and also I would say it looks poor in the sense that it's not a steep climb anymore here, right, compared to the previous one. And if we actually look at the N50 value, how do they look like? Here we had the N50 value of 326,000. If we go to the other, the N50, yeah, it's the same. It's the same, right? Because we reached this here, right? But what I can say from this, immediately from these results like this, is that this pre-processing, well, it didn't help. It didn't do any good. It didn't do any bad either. But it was basically the same, right? So it wasn't, if any effect at all, it's really, really small in this case. And I have to say this is not too uncommon. This pre-processing is, well, it's not that super important. It's the removal of adapters. But in this case, there wasn't very much adapters, obviously, right? Because it didn't change. But removing adapters is usually a good idea. Okay, let's have a look at the Quast results from the contigs we got from the nanopore data. right? We assemble them with Canoe, and then we run Quast on them as well, right? In the same way as we did. I mean, any set of contigs you can use Quast for, right? And we have also the same reference genome because this was from the same type of data. So let's have a look at this report. And here is the report from this one. So if I open it here, and here we can now see immediately the genome fraction is 100%. So this looks a little bit better than for spades, right? And the Illumina data. We can also see here that actually Canoe manages to put this into two contigs. We know that the reference consists of two genomic sequences, right? A chromosome and a plasmid. And we can see that this is almost exactly the same results we get from Canoe here. One very long contig here, which is almost the whole chromosome. Can you see that? Here, 5,003,358, while the reference is actually 5,411, right? And then if we go out here, it added a little bit more on both the reference and the second contig. So this looks very promising, right? This was also something we never, this information that there are sort of a chromosome and a smaller plasmid, if you can trust it then. But at least that's something that the Canoe results indicate, that the spades result never indicated, because there were many contigs, right? And it was impossible to see sort of that it was actually two different molecules in here. So this looks very much better, and it is usually better to have nanopore or long reads are easier to assemble than short reads. This is almost always the case. Even if the long reads have much more errors in them. And here we can see that it is not really a perfect. First of all, we see that it's not actually 100%, even if that's the report up here is sort of a rounded value, right? You can see that the contigs are a little bit shorter than the reference. So we don't reconstruct the whole genome. And we can also see here at misassemblies, there are actually 3 misassemblies here. So it's not like these have been perfectly reconstructed, this genome. And if we extend the report here, there is more details on the misassemblies. We can see that there are 3 relocations. And it's in this long chromosome contig, right? There are 3 places here where the Canoe has glued together, you could say, the reads in a wrong way, such that we have parts of the contigs that either has, there is some part of the contig that is wrong, you could say. You can see that so relocation means that one part of the contig is matching in one place and another part of the contig is matching another place, and there is more than 1,000 bases gap, you could say, in between these matches. If you look at my lecture on this, you will see some example of this relocation. So it means that even if this value here looks very promising, 100% and blah blah blah, it's not 100% reconstruction, right? But it's pretty close and better than what we got with Illumina and spades.